Today we're going to talk about the non-regular case of Gaussian elimination. So remember, the regular case was when all the pivots were non-zero. So the non-regular case is when that doesn't happen. When you come across a zero pivot, what do you do? So here's an example. Just take this matrix. Right off the bat, you're stuck because of this pivot. In the first place, this upper left-hand corner entry is 0. If you try and write the LU decomposition of A, you're going to fail. And the problem, as I said, is this 0 pivot here. You just can't start the algorithm. You want to use that 0 to kill the one below it, but you can't. So what do you do? Well, let's see. This really is a problem. Let's just try and do it by hand. Let's try and write A in the form LU for some arbitrary L and U. And, well, if you take A, L like this and U like this and multiply them out, you get B, C, A, B, and I don't care about the lower right-hand corner. And can we find A, B, C, and D to make this equal to this matrix A? Well, let's see. Comparing it term by term, we have to take this B to be 0. So, okay, let's do that. But then this lower left-hand corner, it becomes 0. And I'm stuck. Doesn't work. So there simply is no LU decomposition for such a matrix. All right then, so what do we do? Well, it's not so serious. Why don't you just switch the two rows? Because that would solve the problem. If you switch the two rows, that's a row operation. That seems kind of okay. And if you switch the two rows, it's going to turn it into this matrix. You just get the identity. And that's fine and dandy. That's upper triangular. So that's the key point now. We want to allow an additional operation, which is switching rows, and that will enable us to do more. Okay, so let's see how that works. Let's look at an example, a very simple example. Take this 2 by 2 matrix, which is bad because it has a 0 pivot. So the first thing that you do is you switch. Here's the 0 pivot. So you switch the first and second row in order to fix that. And you get this. So the point is that switching two rows is the same thing as multiplying on the left by this matrix with ones on the anti-diagonal. Okay, so now we're done. This matrix is upper triangular. And the new operation is multiplication by this matrix P here. And this is called the permutation matrix. So we're going to expand our arsenal now and not just use L, lower triangular, but P. And we're going to, well, in this case we wrote PA is equal to U. More generally, we're going to need both P and L, and we're going to get decomposition like this. So this is called the permuted LU decomposition. So again, this is like the previous one. The permuted LU decomposition or factorization. L is special lower triangular as before. U is upper triangular as before. And the new ingredient is this P, which is a permutation matrix. and I will explain what a permutation matrix is next. Okay, so here's the definition of a permutation matrix. So permutation matrix is a matrix of a very particular form, and it's a matrix with the following property. It has exactly one entry, number 1, in each row and each column. So if you look at a row of the matrix, it's all zeros except for a single 1, and every column is all zeros except for a single 1. So let's write down the 2x2 permutation matrices. The only possibilities are this and this, if you think about it. What about the 3x3 permutation matrices? Well, you can put the 1s on the diagonal and zeros elsewhere, or you can keep the first one and switch the other 1s around a bit. Or another thing you can do is you can put the 1 in the second place, and then you have 2 choices for the remaining 1s. So these 2. And finally, if you put a 1 in the first row in the third place, there are 2 ways to fill it out. And that is all of the 3x3 permutation matrices. So here's a question for you to think about. How many n by n permutation matrices are there? That's a good question, and we are going to talk about that in class. Maybe many or all of you will figure it out between now and then. In any event, the reason these are called permutation matrices is the following. If you take a permutation matrix and you multiply it times a vector, x1 through xn, what you get is a vector with the entries permuted around, maybe in a different order, say x3, x2, x1, and so on and so forth. So it's just the same entries, but they get permuted. And so this, another way to say it is a permutation matrix is acting on these vectors by permutations. Okay, so let's just write down a very simple example. If you write and apply this to ABC, you get CBA, and there's a misprint in the video here. Switch the first B and C to make this correct. Okay. So here's a basic fact, which is essentially the same thing as what I just said, it just applied to matrices. If you have an n by n matrix A and you multiply it on the left by a permutation matrix, what you get is a new matrix where you've simply permuted the rows of A. So remember, multiplying on the left does row operations, and it's behaving the same way on each column, which is to say it's permuting the rows. So let's just do a simple example. If you look at this permutation matrix applied to a random 3x3 matrix, what do you get? Well, let's see. When you do the first row, you pick out the first row of the of A, and then the third row, and then the first row. So this is a cyclic permutation. It took it took DEF and moved it up. It took ABC and moved it to the bottom, and it took GHI and moved it up. There you go. All right, here is a question. Suppose you have an n by n matrix, and I allow you to do two kinds of row operations to it. The kind we've been doing all along, which is adding a multiple of one row to another, and another one below, I should have said, as usual. But now I also allow you to permute the rows. So is it possible to get to a matrix like this with all the AIs not equal to 0? We saw before, of course, that the answer was no if I didn't allow permutations, but now if I allow permutations, there are more matrices that I can put into this form. And I'm interested in looking at what matrices this works for and how you go about doing that. So that leads me to what I'm calling a temporary definition. It's temporary because it's not very satisfactory. I don't really like it. It's a little bit circular. You'll see what I mean in a minute. So you have a matrix A, which is n by n. We say this is the definition, it's non-singular if the answer to the previous question was yes. So that is to say, we say A is non-singular if the following condition holds. If it can be put into, reduced to this upper triangular form, A1 through AN with zeros below, using the previously discussed operations, which is to say both kinds, including switching rows. And of course, I'm asking that these AIs be non-zero. So, well, this is kind of circular because I asked what matrices this works for, and I just said define non-singular to be the ones that it works for. What good is that? Well, the point is that in the next section we're going to see a theorem which describes these matrices in a different way, and many of you, I'm sure, are familiar with this notion. It turns out that this concept of non-singular is exactly the same thing as saying that the matrix is invertible, and that's exactly the same thing as saying that its determinant is non-zero. So that's getting a little bit ahead of ourselves, but I wanted to say why this is kind of a temporary definition, because it's going to be replaced by something which is better shortly. Okay, so the main result here is the following. Suppose you take an n by n matrix. If it's non-singular, well, it is non-singular if and only if it has a permuted LU decomposition. That is to say that that you can find matrices P, L, and U such that PA is equal to LU. And, well, this is almost obvious from what we've been talking about. Let me just say a few words about that. So this, how do you see this? Well, this L is the adding multiple of one row to another operation, always down, of course. And the permutations are here. If you need to switch rows, you put that in P. And so together, that gives you this decomposition. Now, the only thing is, there's a little bit of a tricky point about what order you're applying these operations in. Because when you do the algorithm, you might switch some rows, might add some rows to other rows, and then switch some rows, and then do some more adding, and then switch some other rows, and the P's and L's could get mixed up together. So there is a little bit of an issue there. And, well, the resolution to that is you could have done all of the row switching first and then do the LU decomposition. So let me illustrate that with an example. So suppose I asked you to find the permuted LU decomposition of this matrix. Yes, this matrix, 1, 2, 4, 0, 1, 0. And, well, you go on your merry way. You can start the algorithm because you have a non-zero pivot up in the upper left-hand corner. So you use that to kill the one underneath it. And by adding minus the first row to the second. And you get this. And now we're in the situation where we have a zero pivot, this zero right in the middle here. So what I've done is this is an L. I've taken A to L times A, where L corresponds to this row operation. Now I have a zero pivot, and so in order to fix this, I need to switch the second and third rows. And after I do that, I get to 1, 2, 3, 0, 1, 0, 0, 0, 1. And how did I do that? I multiplied on the left by P. So I get this. PLA is equal to U. And that's almost good enough, except the P and the L are in the wrong order. I kind of wish that I could get that L to the other side, but I can't. So let me say a little bit more about that on the next slide. So I have this, I'm trying to get this L over to the other side, but it's a little bit of a problem. So I have this PLA is equal to U. What I wish I could do is multiply on the left by L inverse, and that would get an L onto the right-hand side, or L inverse. But the problem is this P is in the middle. If it wasn't for that, the L inverse and the L would cancel, and I'd have A is equal to L inverse U. But now I have this ridiculous thing here, L inverse P, L times A, blah, blah, blah. It's no good. It just, you can't really fix it. But the way you fix it is you see, well, I should have switched the second and third rows first. I had to do that eventually anyway, so do that at the beginning. Apply P first. So when you do that, what you get is 1, 2, 3, and then 0, 1, 0, and 1, 2, 4. And now you can see when you do the rest of the LU decomposition, there won't be any zero pivot problems. So at the first step, well, you already have a 0 in the second row, so you only have to add the third row down. You multiply that by minus 1, and what you get is 1, 2, 3, 0, 1, 0, 0, 0, 4, and that's good. Excuse me, 0, 0, 1, and that's good. So now what we've done is if we take L to be the appropriate matrix for this last step, let's write that down. L is this matrix with a 1 in the minus 1 in the lower left-hand corner. I've got LPA is equal to U, and now I can bring the L to the other side. And, excuse me, I have PA is equal to L inverse U, and that's good. I can replace that. That's my LU decomposition. So just to write it out, I have that PA is equal to this times this. Here's U. 1, 2, 3, 0 with 1s. Yep. So that's the moral of the story, is to do all of your permutations first. And that can be a little tricky in large examples, but it works. So here's the conclusion. You have an n by n matrix. It has a permuted LU decomposition. PA is equal to LU. If and only if, after permuting the rows of A appropriately, all of the pivots are non-zero. And furthermore, you can arrange to do all of the permutations first. Okay, this isn't so good. The problem is, you'd like to know if a matrix has a permuted LU decomposition, this says you have to run the algorithm and see. And maybe you can do it and maybe you can't. But that's you don't want to have to run the algorithm. You'd like to be able to just glance at a matrix and tell. And in the next section, we'll talk about that. That's this business that these matrices are exactly the invertible matrices, and you can see which ones are invertible by just checking the determinant. See you in class.